Okay, let's consider a particle being pushed by a force. Okay, Newton's second law would say that that force caused that particle to accelerate. Okay, and let's just assume for simplicity one force, but this could be the same thing. We put F net, and that would be the same thing. And let's focus on just one direction right now. Let's say Fs equals MAS. Okay, so we'll focus on one component. So this force is pushing this thing in this one direction. All right. So what we're going to do is show how Newton's second law can be rewritten as conservation of energy, or better yet, in this particular case, the work kinetic energy theorem. We need to start to remind us that we started by assuming that we're acting on a particle. So our system is just a particle. Just one particle. All right? Okay, now for a bulk of what we're going to do is just some math trickery, or just some math wisdom. It's not necessarily tricks, but it's some wisdom with our math to see how these variables relate. To start, I'm going to remind myself that acceleration is just a change in velocity over a change in time. And if I take those time intervals to be super, super small, then this would be the calculus limit, and I can apply this even if the velocity is changing over time. Okay? And so I'm also going to do a trick here. I'm going to multiply this thing by 1. And my 1 is going to be a fraction with the numerator being ds and the denominator being ds. So that's just number 1. I can do that. If I multiply the top and multiply the bottom by the same thing, that's valid. Now, this is the beauty of thinking about derivatives physically. These are just really small changes. So this is just a fraction of a small change over a small change. This is a small change over a small change. Okay, so I can rewrite those fractions and swap those denominators. They're just two numbers. I can swap them. And so I have m dvs over ds times ds over dt. Okay, I'll put parentheses around this just to keep it clear. I'm just multiplying these two fractions. But what is ds dt? It is the velocity. That's just the velocity in the s direction. Okay. Now, what I want to do is trying to explore this. I want to look at, well, what's happening with the velocities alone? Not worrying about the change of position, but just what's the velocities doing? Remembering that this is just a fraction, I can multiply this ds up to this side with the force. So doing it, I can have fs ds equals mvs dvs. Okay. So this is mass times the velocity times a small change in velocity. Okay. Well, that would be something I could look at now. This is all about velocities. This is about positions in the force, and I can see how they're related. But I want to try and focus on a large change, a full process, not just a small change. But to do that, I'd have to integrate. Okay, so I can't consider just the small change. No, I have to integrate that. And if I integrate that side, I have to integrate the other side. Well, this is changes in position. So I'm going to go from some S0 to S1. This is changes in velocity. So I'm going to go from V0 to V1. Now, these limits are connected. Even though this is all about velocity, this is all about position, this is the velocity at S equals S0. This is the velocity at S equals S1. Okay, so they are connected. All right, now, focusing on this right side, what is the mass is a constant. It comes out, and I have an integral of Vs with respect to Vs. Well, that's just going to give me a 1/2 Vs squared by the power rule. So this ends up being a 1/2 m, the m came out, Vs squared. And I evaluate it between its limits. Okay, so from V0 to V1. Doing so, I insert the top limit, which becomes V1s squared. Then I subtract it, evaluate it at the bottom limit. That's V0s squared. Okay. And this quantity here is what we call the kinetic energy. That's K1, kinetic energy of the particle at this final position, or final state, and minus K0, kinetic energy of the particle at its initial state. Or, in other words, this is just the change in kinetic energy of the particle. Okay. Now, this is pretty powerful. This, all I care about is its initial and final states. I don't really care about how it got there. I took care of that. This is independent of any other dynamics. This is just how fast is it going. And so this integral holds true no matter how I got there. And so this is true no matter what the process was of getting there. I could have gone slow to start and then fast. I could have gone fast to start and then slow. It doesn't matter. It just all that matters is the initial and final states. Okay. Well, what's this other side? We'll get in this more detail in a later reading, but we define this, which is basically force times the distance, but more particularly the force in the direction of that displacement. Okay, so force times the displacement. All right, and we call that work. Give it the symbol W. Now this is what the environment is doing. This is dealing with my particle. So this is the environment acting on the particle, or the environment can cause the particle to change its kinetic energy by doing work, and it equals that change in kinetic energy. This is called the work kinetic energy theorem, but it's very limited. It is only true for a system of a particle, but that's often the case. We can often figure that out, and so we can do that a lot. And so if we can find the work done on a particle, then we can find out how it's changed speeds without having to do any more calculation, any calculus or any integrals or anything like that. We can simply find this delta K. Now, finding work may not be easy of itself, but there are many cases which it is. Okay, so we're going to focus on this right now, but remember, it's only for a system of a particle.